So we'll do the right-hand side first, and we're going to do the right-hand side first because it's the easy one for two reasons. One, because it's only got one arbitrary function in it, the basis function, and secondly, because there's no derivatives in the right-hand side. So that makes things easier. And so each entry of fi is, remember, the integral over the whole domain of this. And so we can do the same stunt we talked about last time. You split the domain up into chunks. Integration is a linear operator, so it's just a sum over all of the chunks. And that matters computationally lots, because the entry fi corresponds to the integral of phi I times this thing on the right-hand side. And phi I is 0 in almost all elements. Right? So phi I is the basis function corresponding to one global node. And global nodes live on the topology somewhere. So they're either on a cell or on an edge or on a vertex. So in the very worst case where they're a vertex degree of freedom, they're only non-zero in the approximately 6 triangles that meet at that vertex. And they are 0 everywhere else in the mesh. So this integral is very, very sparse. Yeah?
Why did you say 6 triangles?
Because on average, so you can have an arbitrary number of triangles meeting at a point, but if your mesh generator is being well behaved, it will try to make triangles that are approximately equilateral, because all of the errors will come out better that way. And 6 equilateral triangles meet at a point. So if you have a reasonably high quality mesh, there will be about 6 triangles meeting at each point. So what we actually do then is we don't assemble this vector by visiting each entry of the vector in turn. What we do is we visit each cell and we make a contribution to all of the degrees of freedom that touch that cell and add that into the corresponding bits of the vector. And so we visit each cell once, and when we've visited each cell once, we've built all of F. So you do it that way up. And that's because that's the efficient way round, right? When I visit a cell C, I have a known number of degrees of freedom. All of those are non-zero here. I can do the calculation for those, and I know where to put them because I've got the cell node map. And that way round is a very efficient way of doing it. So the way you do it is you start off with fi being 0 everywhere, and then you visit each cell. And in that cell, you integrate the local basis function, and that's multiplied by f in the local space, and f is nothing other than the local basis functions times the right global coefficient. So that's exactly what we did in number 5 to do integration. So you do that by using the cell node map to look up which of these coefficients should I use here. You do that multiplication out. There's the change of coordinates, Jacobian, that we talked about last time, because it's an integral. And what you need to do is that will produce a number of contributions to integrals equal to the number of i-hats, i.e. the number of local basis functions. And you need to shove those, add those into the right entries of the vector f. Which of the right entries? The right entries are given by the cell node map. And then the last thing you need to do, and the last thing I'll talk about today, and we'll come round again tomorrow to talk about the left-hand side matrix. So we talk about it in total 3 times. We do integration, and then we do integration of vectors, and then we do integration of matrices. And so hopefully by the time I explain a slightly more complicated version of it 3 times, it becomes unintelligible. So to get from here to here, we just have to do the standard numerical trick of turning an integral into a quadrature sum. And so all I'm doing here is, having chosen a suitable quadrature rule, I replace the integral by sum over quadrature weights. I evaluate any basis functions I might have at the quadrature points, and I multiply once again by the change of coordinates, which, as we discussed last time, is constant over the self. And that's it. So that guy is the statement for how you build the right-hand side of a finite element problem.